Okay, so we can start. So we were doing a diffusion model, and these are the we already did the first two one, training and inference, but there are slight variations also. So those training and inference algorithm will change a little bit. And we have seen signal to noise ratio interpretation, so that helps in scheduling of the noise. And so these are the things we did in the last class. So basically the iterative algorithm is quite simple. So until convergence in the loss there was sum over the time step, but that sum could be also kind of replaced by expectation over uniform 1 to t. So you can pick some t randomly, uniformly from 1 to t. So these are the slight changes from the original loss. And so t is uniformly sampled, and xt is sampled from normal, and these are the mean and variance. Obviously mean depends on alpha t, variance depends on alpha t, and alpha is the scheduling that we do via a signal to noise ratio estimates. So we know how to sample because we know mean and variance of a normal distribution, and we sample time step. So you have this sample xt, and this sample xt is constructed for a sample t. Okay, so out of 1 to t, let's say the 10th time step you sample, so you will generate x10, and you know that because these alpha are kind of known, so you will generate that, and xt is known. And now the goal of the denoiser is to predict the original image, which was x0, from the current time sample xt. Okay, so this is trying to predict the original image, okay, from arbitrary time t. Okay, and so it is expected that in the training you will see through all possible times, because you will run this many times. So you will kind of learn from arbitrary t to get to predict the original image in some sense. This is via training, but inference doesn't happen in one shot. That's the thing. Okay, when you do inference, then you go from t minus 1 and so on. But while doing training, you do it like this. From arbitrary t, you are trying to predict x0. Okay, so because this is a common neural network. Okay, so this neural network doesn't change at each time. This is like CNN, right? It's so same neural network is learning from t to x0, okay, or some other t prime to x0, and so on. Okay, there are proposals that can you keep these different at different time steps, and some proposals where that when the denoiser is trying to kind of do the denoising, then there are bit of dynamics. Okay, in some of the papers what they propose is that it is good to have kind of different denoisers in the middle range of the denoising step in the early stages when you are taking it from let's say the prior or like in this case it's not about prior, it's in this case it's about like this training. So so what they see is like in the early stages, in this stage and this stage, the denoiser that you are training like this, you may opt for different neural network here, here and here. But what we are saying in the basic one, DDPM, is it's the same neural network. It's learning at time xt to see if it is predicting correctly. From here, whether it's predicting the x0 correctly, and so on. Okay, so what you see from the loss and what is done here, there is a slight difference. Sum is replaced by uniform, and you're trying to kind of predict. But this happens only during training. When you are generating, you necessarily have to go like this, otherwise it doesn't produce good images. Okay, so this is how it is trained. So as I said, sum over t was now replaced by expectation. Okay, because sum is essentially average, right? So so you can think of average as some it's an arithmetic kind of mean if you divide by the total, right? But so you can think of that sum sometimes as expectation over. Yeah, so this is the illustration of how training is happening. So obviously during training real images goes in, and you have some noise component, and then your original image is x naught, obviously, and you are trying to predict, having arrived at x1, you are trying to predict, can I predict x naught from here? Having arrived at xt, you are training a neural network. Can I predict x naught from here? Okay, can I predict x naught from t minus 1? This is just the second last step, right? Until it becomes a pure Gaussian noise. So we expect that it is. Now again, here also there are quite a few papers. We will go into diffusion model engineering in the last class. So we will look into a lot of engineering aspects. But yeah, so from engineering point of view, there were papers they were saying, like, in some papers they were, because it's an iterative method, so it was like as if they were not really going into exact zero. Okay, so there are papers that are saying that these papers, due to iterative method, they just stop at 0.001, but we ensure that it goes exactly to 0.1, and that has some effect and so on. Okay, so we will come back to all these things, these minor engineering things. We will come back to a bit later. Let us look at the global picture. So global picture is kind of easy. Okay, given an image at x naught, you train a neural network to predict that at x2, and obviously you will train in batches. Okay, it's not like just one image went in and you will jump to kind of you send batch of images, right? So whatever your favorite dog or cat, right? So you will send a batch of that, and then build a loss over the batch. Okay, so and you will do it multiple times, because so batches should will be small, right? So small part of the training data, it will go through one epoch, but you will repeat also. So it's a second iteration, same image might come back again, just like the usual neural network training, right? Same examples can come back in some other batch and so on. So that's the usual training that you have to do. And inference is like how you now start generating. So in inference, what has been observed is like you really have to go one after the other. Okay, you cannot really jump from t to directly to 0. Okay, so there have been some papers that try to do that. There are papers like consistency model and things like that, but the original idea is that during generation you necessarily have to go t minus 1, t minus 2 up to 1. Okay, and obviously these things are known to us. Neural network has been trained, and this is known to us. Obviously, to create a variation in the generated image, we always have this initial noise vector, and this noise vector will be kind of, it's a random sample, and that is the reason why the generated images have some novelty. Okay, if it started each time from something fixed, then you get something fixed. Okay, because starting from something fixed, neural network by itself doesn't generate anything random. If you give something fixed after training, it will give you something fixed. The novelty is coming from the fact that you are sampling from, at t you are sampling from something which is from standard normal, but some variations is there, and these variations get propagated, and you will end up generating some new cat image. Okay, so inference is kind of easy because everything is known to you. Alpha is known, neural network x hat theta is known at xt because you have trained that. Okay, so and then sigma qt is known, it's a variance, and that is defined by alpha t again, and z you sample. Okay, so inference is also kind of easy. So obviously the missing piece was alpha t, and we saw some guiding principles in the last class that you should formulate it as signal to noise ratio. Once you have that guiding principle, then you choose anything that turns signal to noise, like almost anything. Okay, there is no such strict thing there. Now how you can reduce, one thing is sure, you have to reduce alpha t, because you have to go to zero mean and variance 1. Okay, so the way we define, if you remember, alpha bar goes like this. So obviously this we have to tend to 0, right? So xt is kind of defined like this, plus 1 minus alpha bar, variance is defined like this, right? Yeah, something like that, right? So basically, you know for sure that alpha bar t, if it goes to 0, then you're going to kind of standard normal, and so a good view is like signal to noise ratio kind of thing. So we did that in the last class. Let us skip through these derivations. We did it in detail. So this is the derivation we did, and we arrived at this. And this happens to be SNR, because this is the mu, and this is the sigma. So mu square by sigma square is SNR. Okay, so this tells us that you should look at kind of going from pure signal to pure noise, basically. So basically decreasing this value, basically. So overall what it means is that your alpha t should gradually go to 0. Okay, then SNR is going to 0. Okay, and you're getting to pure noise. Okay, so overall our loss then looks like this. So from here there are many ways. Okay, and many papers discuss various dynamics that I'm choosing alpha t decay like that, and I observe this and so on. So again, this goes into engineering domain. As far as maths is concerned, we know that any decay would be good enough from like theory, but from engineering point of view, you play a lot. Okay, some scheduling cosine, some decay. Okay, some decaying function you choose. So we will try to fill that in the last class. Okay, some explicit thing, but from our point of view, it has to be decay. So I will give you one way that it could be kind of event trained. So although we said that it's not required in the forward pass, we don't want anything like that, but one possibility that you may train that. So what you really want is SNR is something that has exponential decay. I mean, that's something I want, let's say. Okay, I want it exponential decay of some with respect to some weights, which I will learn via some neural network. Okay, so this, as I said, this is one possibility. Many papers don't do that; they just go for any decay. Okay, so again, there are many choices. It is just one possibility. If you just do some algebra, then it turns out that alpha t could be defined like that: 1 minus sigmoid of. So you know the sigmoid function. So basically you choose anything that kind of decays over time. And it could be something explicit that you don't know, like W weight or something. Let the neural network learn these weights, and you get this scheduling also trained kind of. And if you are not comfortable with this, then as I said, choose any monotonic decay that works in practice. Okay, so that's not a problem. Okay, scheduling, you just call various type of scheduling and it can happen. So, but as I said, there are variants of these. So what we have seen is that in our loss, training loss, we have a neural network that predicts the image, the original image. So in this variant, we predict the original image, okay, which was our X node. So from here, intuitively, you can say that what if I predict the noise itself? Okay, so my noise, so I built a noise predictor rather than the image predictor. So if epsilon was the noise that was added in the that is being added, then can I kind of learn just to denoise, right? So that's another variant. So we know that xt at a given time t is can be written using reparameterization technique, because these are Gaussian. So I know that I can sample from standard normal, and by scaling of the mean and variance with the standard normal variable, these xt's are obtained. So from there you will bring in these epsilon node. So let us see this. So there are three avatars. Like these are the three. Okay. So you will see three variants of DDPM, denoising diffusion models, and so this we have done already. And in this second variant, we are saying let us predict the noise itself. Okay, and this looks not so intuitive. We will see that this is called score matching. Okay, so this is kind of called score, or so we will see that as well. But let us see this now. Okay, so as I said, this is kind of easy because I just have to write xt in terms of kind of, you know, the formula that we wrote. Xt is like square root of alpha bar and so on, and recursively it goes up to x naught, because xt is anyway, right? Xt comes from xt minus 1, xt minus 1 comes from so on, and x naught. So it is indeed possible that I can write in terms of x naught, and just the first noise that was added, that's where we have to go, right? And somehow we bring in that epsilon naught, and the denoiser, anyway, you know, it cheats in a very good way, and it will just look at this part and try to predict that, and remaining it will match exactly like the true denoiser. Everything just comes out as constant. So let us do the same thing. So now it's the second avatar is like predicting the noise itself. So as I said, the way xt propagates, this is the relation we have, starting from x naught, and the first noise that we introduced, which was epsilon naught, the xt current sample could be written like that, right? So this is the way we propagate, right? So this is our plan from the beginning, right? And from here, x naught we can solve. Okay, so this comes from here, and now first step, as we had before, is derive the ground truth denoiser mean. So this is the ground truth denoiser mean, and so this expression is for the ground truth denoiser mean. We know that we did a lot of calculation like that before, but here we will replace x naught from here, and once we replace, we get this. Okay, so this is a simple direct substitution, and other terms don't change. Okay, and after that there will be algebraic manipulation. So first one seems to be the same. Second one, there seems to be something happening. So what is happening here is, if you see this guy and this guy, this guy is like square root of 1, I mean alpha 0, alpha 1, alpha t minus 1. So this bar means like product up to t minus 1, and this guy is product up to t, right, alpha t. So basically this guy has just one alpha t. So if you break this part, square root alpha t, and this is alpha bar t minus 1. Okay, so the remaining one up to here t minus 1. So basically this will be square root, right? So what you see here is that there is this square root and there is this square root, and they get cancelled. Okay, so hence you are left with only alpha, sorry, not here, but only alpha t here. Okay, so we have this, and this guy is already as it is. We did not change anything, and we did not change anything on the numerator. Here it is intact. So that's the only thing we have to do. Now it seems like we split the fractions, I guess. So here, if you see, we pull this out. Okay, so this is this guy, right? And then we pull the second term here. Okay, so this is this guy. This is this guy. So 1 minus alpha t xt, 1 minus alpha bar, and this also actually. Okay, that also came here. And remaining term came here. Okay, so this is simple algebra. So remaining term is 1 minus alpha t, square root of 1 minus alpha bar epsilon naught, and this 1 minus alpha bar was there, and square root of alpha t was here as well. Okay, so we have this. So we will copy it here. The same term, last term, is copied here. Now, so basically now what we do is we multiply, because we want to make this same denominator here. So we multiply and divide by square root of alpha t. Okay, so here, okay, because we multiply and divide by square root of alpha t. So since we multiply and divide by square root of alpha t and square root of alpha t, then this square root of alpha t, this square root of alpha t becomes alpha t, and then we have this square root of alpha t here, and this guy remains the same, and this gets. So one of the square root gets cancelled, so we are remaining with 1 minus square root of 1 minus alpha t, and these are as it is. Okay, so so here if you simplify this guy, then alpha t minus, so if you see this guy with this guy, right? So they together make alpha bar t, right? Because alpha t and this guy is product up to, because there's a bar, right? So product up to 1 to t minus 1. So together they make it alpha bar t. Okay, and basically we have taken the denominator common as well. Okay, so this is the common denominator here, and we have also kind of added this guy here. Okay, so this is simple algebra, nothing here, and this is just copied over. And here it seems like there is a cancellation of these alpha t and alpha t. So we are left with 1 minus alpha bar t, and denominator is as it is, and this seems to be as it is, and yeah, so this again, one of these guys got cancelled, this got cancelled, so I got this, and this is as it is. Okay, so this is the final form. So we substituted x naught and then we arrived here. Okay, and so our goal was to bring in this epsilon naught. What was the first noise that I added, right? So we want to derive the second key. So this is the form of the ground truth denoiser. So if ground truth denoiser is like this, then you know what the approximate denoiser is going to do, right? All along it has been cheating again, and so it will cheat, and it will be everything is same here, everything is same here. Now it is focusing only on this, okay, because these things are anyway kind of known. Okay, so now it is supposed to only look at predicting the first noise that was added, okay, from any time step t. Okay, so that's the thing, because so now we will go to KL divergence and check with KL divergence that with this mean variance they always keep the same, right? So the only mean kind of changes. So the KL divergence between these two Gaussian will be difference of the means. So that's the general derivation we did. So we employ the same thing here again. So we go for the KL divergence and ask from KL divergence that with the current mean, ground truth mean, and the cheated one, right? So how do they what do they mean, right? So what is the difference basically? So we have done this derivation before, that given to normal distribution, specifically when the means are same, which is the case in our case, and when only the mean changes, which is the case in this case, then basically it's the difference of the mean. So this is the mu theta mean, and this is the mu q mean, okay, the new one. So that's what we did, and we have this mu theta calculated just now, and mu q also calculated just now. So the way things was done, these were anyway common for both. So obviously these will get common, maybe simplified a bit. So everything essentially will boil down to this after some simplification and so on. So basically these constants anyway come out, and our focus is basically here. So then our loss is of this form, where there is a neural network that is trying to predict the first noise that you added in the image. Okay, so as such it's also kind of easy to implement. The neural network is just predicting the first noise, that's it. So, and in some cases they found this variant is better, okay, although it is it looks numerically equivalent if you ask, because this epsilon naught also came from x naught, so we didn't do any kind of approximation as such. But numerical point of view, sometimes doing things in a different way, although they are equivalent on paper, and gives different results. Okay, so it was found in papers that this variant was a bit better. Okay, so again we are not going to kind of write down the algorithm again, because it's very similar, just like x theta t was there and x naught was there. It's just flipped, but it doesn't matter, because in the norm you do x minus y, y minus x, doesn't matter, right? So the algorithm that we had, wherever you had x naught you put epsilon naught, wherever you had x theta hat you put epsilon theta hat. So essentially the algorithm is the same. Maybe this got changed a little bit, okay, but from optimizer point of view, this is a constant, so this really doesn't really play a role. Okay, that's why in the training you see only this guy you are worried about. Okay, so because we are only worried about argmin, right, the place where the minima achieves. So place where the minima achieved for constant times x or fx is the same, right? So argmin for constant time fx and fx is same. Okay, so that's why we can throw away this constant. Okay, so this is pretty much same. Now let us go to scored function, okay, which is like more popular. Okay, so and kind of simple, again same form, everything, the base is already covered. Now you will keep playing around with the different means. Okay, now here we can use something called Tudy's formula from statistics, and what this formula says is that if you have a sample z taken from normal with mean mu z and variance sigma z, then the expected mean mu z given the sample z will be given like this. So this is kind of an estimate of this sample that you just drawn. Okay, so you are asking, I have drawn a sample, and what is the kind of expected mean from there. Okay, so they are related like that. Okay, so it's like z plus variance, and then the gradient of log of the PDF, okay, corresponding to this. Okay. So in our case, how we are going to use this? So we will apply this to predict the true posterior. So that's what we do usually. We always start with the ground truth. So we will see what this has to tell us. So this is our noiser, and this is the form of the noiser. And so by Twitty's formula, if we want to use here, then we can say that given the sample xt, what is the expectation of mu x? Okay, so then it will be just from here, it will be xt, because in place of z I have xt, so xt plus 1 minus alpha bar t, because that is the sigma that is here. In this case, its sigma is this, and then we have gradient log of pxt. Okay, so we just looked at the Twitty's formula, and we are just saying what is the expected mean of these. Like, they are related like that, right? Look, if you can sample from something, then you kind of maybe know the mean, right? So but what we are seeing is like they are related like that, and this relationship with the gradient of the log of the PDF, this is what matters for us. Okay, so what we have been doing so far is we had some x naught here, we have some epsilon naught here, but now you see something else is showing up here. Okay, like roughly. Okay, so we will see, we will make it precise. So we denote, let's say we drop this, okay, this sub xt, because it's kind of known that, because this is a function of xt, so obviously I'm taking gradient with xt only. So simplification of notation we will assume here, and by Twitty's formula we can infer the most accurate mean mu xt for the originating distribution xt. So in our case, obviously, in our case, the actual the mu xt that we know is this, right? Because the way our xt propagates, if you recall, the way our xt propagates, it follows this basically, right? So this is already written here. So obviously, if you take the mean of this, the mean of this is obviously this, right? So for any xt, our mean is the way we have defined things. It is square root of alpha bar t x naught. So this is something we know, and now we are saying, what if I equate this to Twitty's form? Okay, so the mean that we know and the mean that will come via the Twitty's form. Okay, so they should match basically. Okay, so if they match, then from here I solve for x naught. So if I solve for x naught, I have this. Now we have the form of the ground truth denoiser. Ground truth denoiser has x naught at the last expression. Each time we are doing that, right? The first derivation was x naught, we didn't do anything. Second derivative was x naught, we write in terms of epsilon naught. And the third derivation we are writing x naught as xt was there anyway, plus some grad of log of p. So this guy, as you can see, after some cheating by the approximate denoiser, it will now try to focus on grad log pxt. Okay, so you already get this, right? Maybe with this fee you can derive your own method, right? So this is the process, right? Your true mean denoiser form is there. You are always thinking of what are the ways I can write x naught. Okay, I can see it in terms of noise, I can see in terms of so-called score that this grad log pxt is called, or it could be something else. Okay, whatever statistical result that you know, approximation you know, you can throw in and derive new methods. So this is the ground truth denoiser mean that we know. Now we will again substitute x naught as before by this quantity now, and we do the similar algebra. Okay, so I don't think we have to. So let us do this very quickly. The first term is same, and same thing happened here. The same trick, right? So up to alpha bar t minus 1 got cancelled, so only one last term remain, and this guy is the same. And then square root of alpha bar t, 1 minus alpha bar t, this just pulled out this denominator, 1 minus alpha t xt. So again the same calculations here. So these guys came here, and then the remaining 1 minus alpha t, 1 minus alpha bar t. So basically we are focusing here, and this seems to be all correct. Okay, so then and then we multiplied and divide, I guess. We took xt common, I guess. So we took xt common, and this xt common, and then the remaining terms, there was no change in the remaining terms, I guess, right? So this is fine. And then here it seems like these are same, so they got cancelled and other things are there. Then after taking common, yeah, it seems like here we did that, multiply and divide by square root alpha t, square root alpha t. So this guy became alpha t, and denominator square root alpha t is there, and this remains the same. So basically we make the denominator same. Now we could take the denominator common, and then after taking common, this guy it gets cancelled, it's the same, right? And then 1 minus alpha bar t, the denominator xt, 1 minus alpha t square root of alpha t log pxt. So basically we got this. Now denoiser, approximate denoiser will propose, right? So this is the game, right? And it will come up with its own proposal. It will take everything as it is and except the last term. So will denoiser will do? Obviously denoiser again goes for the same trick. It does everything the same. Now it's saying I will have a neural network s theta that will predict the gradient of the PDF. So this is a bit different approach, right? That's why, I mean, this is score-based matching. It's kind of a different class of methods where you are kind of predicting these are called scores, okay, or Stein's score. So rather than predicting the noise, rather than predicting the corrupted image, you're doing a slightly different thing now. You are predicting the gradient of the log of the PDF. Okay, so this is a slightly interesting view, but from mechanical point of view, approximate denoiser obviously comes up with whatever you propose. I'm going to predict it because neural networks are powerful. Basically, that's why everything is working. So neural network, whether you throw in the gradient data, whether you throw in the noise data, whether you throw in the noise you added, whatever data you propose, right? Neural network are powerful to learn this. So no problem for the neural networks. They will learn this. So with these two proposals, ground truth mean and the approximate denoiser mean, obviously we go to our friend KL again and double check that the loss function is constructed well. Okay, so it's a KL divergence between true mean, basically true denoiser mean and approximate denoiser mean, and we know that it is the difference of the means. Okay, so and then we put in those mu theta of the approximate denoiser mean, and this is mu q. So the way it is constructed, everything is kind of common. The constants again come out, and all the focus is on this now. Okay, so this is the so-called score function. This is parameterized, obviously, because it is supposed to be learned, and this is the true score function. Okay. So again, from implementation point of view, we may do that, but here it is a bit tricky. Here, the question is your standard, the gold standard you have, which your neural network is. This is the level for your neural network, right? So, but what is that actually, right? I mean, do you know this P in first place? What explicitly is your P, and how you are going to compute the gradients? Okay, so it is a slightly more interesting case. Okay, so we will fill those things. Relationship between score and denoising. So they are, although we brought this interesting concept of score, which is gradient of log pxt, but if you do a little bit of calculation, you find out that it is kind of related to the first noise that you added. Okay, so essentially you may kind of work with this. Okay, that's one possibility. So there is explicit relationship, but then we can also understand this from so what does all this mean, right? So score function, grad log pxt, this is gradient with respect to xt, measures how to adjust the data xt to increase its log probability under the true distribution. Okay, so obviously we know gradient points in the direction of the increase of the function, right? So this is telling us how log pxt is varying at some points. Okay, so intuitively from here, moving opposite to the score function denoises the image as the source noise epsilon naught is responsible for corrupting it. So basically, this gradient directions that we are looking for, it's negative of the epsilon naught. Okay, so there is kind of like a interpretation that it is kind of acting like a denoiser. It's like doing the negation of that. Okay, with some scaling, obviously. Okay, so this is one view of that. But what is also interesting is like this area is related in many ways. Okay, so we are looking into many types of relationship with score matching and so on, and we will see score matching has really lot more other interesting things. But somehow it is also related to SGD. Like, so you will say, what is the connection of SGD, the stochastic gradient descent that we use, right? So with the calculations that we had, we know this. Okay, that we just had this, and we also know that these xt's are propagated with this rule, right? So from here we can solve for epsilon naught, and we put this epsilon naught here. So substituting this epsilon naught, as I said, in 1, so epsilon naught from 3 in 1, and then you will solve for xt, you get that. Okay, and in xt, from 2, yeah. So you substitute x naught from here. Okay, so x naught you substitute from here, and then you can write this in terms of xt and epsilon naught. So x naught has been substituted using 2. Okay, and what do we get after all this, right? So then eventually what I get is xt is because this gets cancelled, right? So we have xt minus, and this term is there, minus 1 minus epsilon t grad log pxt, and then there is this remaining term here, which is here, right? And this gets cancelled. Now, if you look at this closely, this is very similar to gradient updates, right? So if I have to minimize a function fx, then the gradient descent method is x you update by minus grad fx. Okay, this is your gradient descent, right? So this looks very similar because xt update is using the OL, and obviously there is a step length eta also in the gradient descent. So let us put that eta. So this seems to be, I can put this as eta, and this is the gradient, and my function fx, I take this as log px t. Okay, and obviously you can say, but there is this additional term here, right? So this perturbation term there, right? So how do we interpret this, right? So if we kind of forget this for the moment, then this is SGD, where your step length is, let's say, eta t, and this is your fx, and you're taking a gradient to that. So basically, what this means, without this term, let's say, it's not SGD, but it's GD. Okay, so let us first remove the stochastic part. Then the theory that we tells us is that it is supposed to minimize log pxt. Okay, so basically this algorithm is an algorithm to minimize this log pxt. Okay, without the perturbation term epsilon naught. And if we do add this perturbation term, it is just kind of like SGD. Okay, so SGD, if I have a function like this, and if I have to minimize, then gradient descent will kind of do a descent like this, right? And it will arrive somewhere here. But SGD kind of is a little bit perturbed variant of that. So it might do like this, then it might do like this. So it will go like this. So basically, if I have a point here, if I see the level curve, gradient descent does like this, and SGD might do like this. Okay, I mean not that much, but maybe I did too much. So maybe like this. But on average, it goes there. That's the point. Okay, on average, it goes there, and GD is kind of smooth. So this extra term that you see here, this will make it go like that, and this has consequence in generative modeling, because perturbation is something that gives you novelty. Okay, so this is an important ingredient, and when we will see stochastic differential equation form, perhaps we have to use the next class first half to formulate that fully. There we will kind of have to look at the stochastic differential equation. So now why I'm talking about differential equation. So this propagation that you see here, this could also be written as propagation via ODE ordinary differential equation. Okay, so the ordinary differential equations are kind of like continuous formulations compared to the discrete case xt plus 1 and so on. So in other words, this could be seen as a discretization of some ODE. So if I think of time as a continuous component, then the continuous variant of gradient descent could be seen as ODE. This ODE propagates this x. Okay, so we will come to that a bit later. So there are a lot of connections, right? Score matching. In the score matching, one possibility is that we can match the score, which is grad log pxt. Neural network will learn to predict the score, and with this, when I look at the propagation of xt, if I expression for xt, then with the score matching view, it seems like I am just minimizing a function log pxt by a gradient descent. And if I have this perturbation term, then it's a stochastic gradient descent. Okay. Now these connections are important, as I said, because you may go into probability flow models, because from here your next step will be because SGD is related to ODE, and ODE has the perturbation, then it's stochastic ODE. So that's how there are further papers on that. We will see that kind of SD in the next class. But for the moment, we have this SGD view. Now all this, as I said, like I already told you, this is SGD. So in this slide, I'm kind of like taking this as eta and so on, like writing this in a more compact form. So, but this is the SGD. This is the gradient descent step, and with this, it becomes SD. Now, this is something that was known in physics community as well. They call it Lanchovar dynamics. So that says that if I have to kind of do sampling, then what is the process to kind of keep generating kind of new samples. So this is one way it connects to Lanchovar dynamics. But so we will see that. So many things are now kind of related: sampling, SGD, Lanchovar dynamics, and score matching. Obviously, score matching is the place where that relates to our case, where we do the generative modeling. So this is what is known in physics community, that there is a Lanchovar dynamics that is used for sampling from a known distribution in an iterative way. Okay, so I want a sample xt plus 1, given the sample I had xt, so then iteratively I can sample from a given distribution pt. So as long as I know how to take the gradient of that PDF of that distribution, then that's all I need basically. So this is not exactly in that form, because if you see the thing that we choose here is eta, but very close, and here I had square root of eta. Okay, so there is just this square root 2 factor that is different, but as you can assume, this will be essentially the same. Okay, the square root 2 is 1.44, just like almost not too far from 1 also. So overall, it is very similar to what we derived before. So in some sense, Lanchovar dynamics is also an SGD for log pxt. Okay, with these step sizes and so on. So basically, this could be seen as kind of this is an update, could be seen as SGD for this optimization problem, right? There is when you look into this, then you should not read this as maximum likelihood estimate. This is not maximum likelihood estimate, because maximum likelihood estimate happens for the parameters of the distribution. Okay, this is the parameter of the distribution, and we are fitting a distribution which is parameterized. Could be neural network, the parameters are mean and variance. So we're fitting a distribution over the samples. That's a different problem. This problem where we are doing log, it looks like log likelihood maximized, right? So but this is not that, right? So this is maximization over the x itself. So it's like the distribution is known to me, and I'm going to go. I want to go to the max modes of the distribution. Okay, where the probability of is very high according to the sample p. So I want to go to that x. Okay, so this is a different problem than maximum likelihood estimate. Okay, so So it's good to know that. And so we want to locate most frequently occurring because that's where the histogram will have the highest mode, right? So typically the distribution, if it is two modal, then they will look like that, and we are going to go to the max of these. Okay, so obviously from optimization point of view, it could be non-convex as long the moment we go for multimodal. Okay, Gaussian mixture models and things like that, then we are dealing with non-convex in the sense that non-convex will may have like multiple maxima. Okay, so obviously from optimization point of view, there is no guarantee that you will go to global maxima. Okay, it depends on your initial guess. If your initial guess was from here, then you will end up at this mode. Okay, because gradient descent stops at local minima. Okay, because gradient vanishes here, right? So if gradient vanishes at that point, you will not propagate the x, right? You just stop there. Your algorithm stops, and you will say, okay, I settle with this maxima, and you will say, okay, this is one of the x where there is a peak. There is a peak in the PDF. But although technically high dimensional multimodal PDF we know is there, so but you hope to get to one peak because the gradient just becomes flat, no signal from the gradient. Because of this, you will just kind of be like that. So you will be kind of a little bit of perturbation will be there, but you will stay there because nothing much will happen. And if you just start from here somewhere, then it will take you up to here. Okay, so you will just kind of stay here. Okay. So so it could be used to draw samples. It is essentially a gradient descent, and this is not MLE. Okay, so we already. So it could be multimodal with many peaks. In general, it will be a non-convex optimization problem. A non-convex optimization problem, we know it's NP hard. NP hard to go to global minima, but obviously easy to go to local minima. Okay, so local minima by gradient descent is always possible, but global minima is NP hard. So you should be happy with whichever mode you hit. If you are not happy, then change your initial guess, and hopefully you go to some other peak of your data. And so that depends on, but there is no such guarantee as such algorithmic guarantee that that will kind of ensure that you go to in a general case there is no guarantee, okay, that you will go to global peak. Okay, so from a geometrical interpretation point of view for score matching, as you can see, we are taking gradients, so this will be some form of vector field, right? So if it is a two model distribution, so PDF is a surface plot, let's say, because this is a surface, right? That's why you get this. So it is at least like XY, right? So that's why if you look at the level curve, like your function is like somewhere above the screen, right? And you are looking at the level curve of these. Okay, so level curves. Let us say I have a function like that. Okay, this is a surface. So this is like function fxy is x square plus y square. Okay, so then the level curve, if I draw, because level curve is a way to see 3D function in a 2D. But basically, so I will see what are the domain points that achieve this height. So it will be like this. What are the domain points that achieve this height? So it will be like this, maybe. Okay, what are the domain points that achieve this height? Maybe like this. So this is level curve. Okay, so if your function is like that, then your level curves will be also like that. Okay, but what is good is that somewhere around the center you have maximum or minimum. Okay, so with this understanding of level curve, this is a plot of some fxy type. Okay, and there is one attractor here and there is one attractor here. Okay, so if it's a maximization problem, then there are two peaks. So one of these is here and here. So these gradients point in the direction of the increase. That's the calculus tells us. Okay, so depending on you want to do the max or mean. In this case, let's say we are doing the max, then we follow plus gradient direction. So in this case, you have like two possibilities. As I said, if your starting point you are here, then your gradient field will necessarily move you here. But if your starting point was somewhere here, these will kind of push you to this minima. Okay, so so basically from a sampling point of view, this is kind of what is going to happen, because our real life data, once you assume that your S theta is known, then you will be kind of sampling, and so basically this is our multimodal data, a lot of mode, right? And what we are mapping via this is, let us say, very simple distribution, okay? Or it could be a mixture also. I mean, it doesn't matter, but it's still simple that I can kind of sample, right? So basically, from here, if you sample, then the dynamics will take you somewhere here, or sometimes dynamics will take you somewhere here, okay? Depending on what Z you pick and so on, okay? As such, there is no direct control, I would say. Like you will sample something from here, you don't know which branch, which of the mode it will pick, okay? You don't know, like essentially, so it may go here, it may go, just like when I'm optimizing a fxy function, I don't know that you will necessarily go to gradient to the maximum peak. I cannot tell you that you go to maximum peak. What I can tell you is that you will go to some nearby peak, right? But as such, even I don't know, maybe in a very high dimensional problem, even we don't know how many peaks are there. Because solving how many peaks are there is like you have to take gradient equate to 0, and that itself is a root finding, I mean, problem. Where are the zeros, right? It's very high dimensional problem. You cannot even know where are the peaks. How many peaks are there? Where are they? So as such, it's tricky. So when you will generate the sample via score matching, you will be pushed via this gradient fields, okay? And you see there are these very critical phases. You came via this, and just with slight perturbation you are pushed to this guy, or you could have been pushed to this guy, okay? This is very, there are these cases you don't know when you will slip here, when you slip there, okay? But nevertheless, it will be some interesting samples because it is going to some of the peak, and since it's going to some of the peaks, it will be some interesting sample, because the likelihood of that, because of the peak, the likelihood of the sample will be relevant there, because so that's how things are, right? So so this is what score matching is doing, right? It's you are following the gradients essentially, okay? And it could be trained and so on, provided gradient of log pxt is like well formulated, right? So there are a few ways people come up with approximations. So what are ways you can compute this gradient of pxt, right? So one possibility is explicit score matching, where you use some kernel density estimation. This is like well-known thing, statistical thing, where basically it is like fitting a proxy distribution qxt over the given sample xm, is similar to maximum likelihood, but now you make use of some kernels, okay? So kernels are kind of like basis functions that some combination of this basis function can fit this, okay? We are not going to use this, but it's good to know that there is a way. But this is not a scalable approach, but it's good to know that we can create a proxy px, basically. In this case we are saying qx. It's a proxy, we give a different name, and this proxy is now this is a proxy for your original qx, okay? So this is the data-based thing that you fit, and these are the kernels, and possible linear combination of these kernels will give this proxy px, so whose gradient you can compute, okay, hopefully cheaply, and then you match the score matching for this proxy gradient of the proxy PDF. So that's the score matching. So these are the place where we just kind of the kernel density estimation we did, and we just put in this kernel density estimator here, and we pull out some constant, we pull out the sum as well outside, and we have this as a loss function we have to kind of train. Okay, so this is one possibility, and after training, obviously, once the S theta is known, I can just follow this to generate new samples. Okay, but we don't typically use this. It's good to know, but let's look into denoising score matching. So in denoising score matching, you see a slight difference here, right? So it is also looking like some proxy, right? Q, but it is conditioned on some x prime. So let us see what exactly this means, right? So we see q x prime x given x prime as some normal distributions x given xt with sigma square. So so with this choice of x, yeah. So given so our x is obtained like this, x prime plus sigma times z. Z is like standard normal. Then let us look at the gradient of this proxy that we have right now, and this is normal. So we have this normal distribution expression put here, So we have grad x log of the PDF of this proxy, which we take it like that. Okay. So now yeah, and mean, the way x is written, right? So the mean mean will be x prime, because if I take expectation of x, then this is expectation of x prime, and expectation of z is 0 because that's from standard normal. So expectation of x is expectation of x prime plus sigma expectation of z. It's like 0, right? So yeah, so for the expectation would be and x prime is given, so x prime is given, then expectation x prime is x prime. Okay, so that's why you see this because we have in normal distribution x minus mu square by 2 sigma, right? So this mu is this x prime here, and x is kind of a variable. Okay, so so we have grad x here because of the log. This exponential term came out, right? And log applied to this guy, so this was 1 over, so it became negative. Okay, so and this is gradient with respect to x. So if we take gradient with respect to s, then this guy becomes this. Okay, half of norm of x minus x prime. If you take a gradient with respect to x, this is just x minus x prime. So that is kind of settled. And then sigma square is there, and this was anyway constant. So this gradient with respect to x went to 0. Now x minus x prime from here is sigma z, right? So then why is there sigma square more, right? There is additional sigma square is there. X minus x prime should be sigma z minus sigma square. Then one sigma will get cancelled, right? The minus z by sigma. I don't see. Do you see why x minus like here itself there is a problem, right? X minus x prime should be sigma z, and one sigma should have got cancelled. And I keep using this, right? So it seems like it should have been correct. Yeah, let us check again. So far it's this, and then 1 divided with this exponential of minus of norm of x minus x prime. So x prime is the mean, and then 2 sigma square, and then when we take the log, then minus the thing exponential and log gets cancelled, and it comes as it is, and then this is like minus log of this guy, and this is certainly 0 because there is no x involved here, and x minus x prime squared by 2 derivative will be x minus x prime only by sigma squared. I think I have to check this offline, I guess, but I will try to fix this maybe. It seems like from our calculation that should have been just z over sigma, okay? Or unless we fix it in the next steps, I don't know. But so it seems like we get this, okay, minus z over sigma square. So if we now look into the loss function, which is essentially s theta minus the proxy score that we have with this q, then we substitute those, and so s theta x, so x is seen as x prime plus sigma z, okay? So that we put here, so x that you see here is x prime plus sigma z from here, okay? So that we have, and the remaining term is z over sigma square, okay? So we still have to kind of double check, but it seems like it is z over sigma square. And then so if we replace this x prime by some x, let's say, which is coming from like the PDF px, let's say, then x prime is replaced by x plus sigma z, and then this is the same, okay? So overall, this is our denoising score matching, okay? And since our x is coming from px, this expectation also changed now, okay? So from q, we started with a proxy, and then we go back to like px, okay? So I mean, there is no harm in that, okay? So we can think of this x prime as sample from x also, okay? So there is no problem. So so this is the final form of the loss of denoising score matching, okay? So how do we kind of interpret this, right? It is looking kind of strange, right? There is a s theta that is applied to kind of x plus sigma z, and then it is kind of matching, it is trying to kind of predict the it is kind of predicting the negative of the z over sigma square, which is the noise, okay? So let us look into this in more detail, okay? So we got these calculations, but let us see this. What does this mean, okay? So this is what we found out, and so the quantity Sx plus sigma z is effectively adding noise sigma z to a clean image x, okay? So that's kind of clear, right? So from a clean image x, we added some noise sigma z. Z is like standard normal, right? So, and the score function x s theta is supposed to take this noisy image, so now it becomes a noisy image, right? And predict the noise z over sigma square, okay? So from the diagram, what does this mean, right? So this is the noise z over sigma square, and then the s theta x plus sigma z is trying to predict the noise, okay? Or let's say the negative of the noise, okay? Because you want to kind of minimize this, right? So we could have written this as minus of z over sigma square, okay? Because in the loss we want to see the negative, right? So we can write the negative of z over sigma square. So basically it's trying to denoise, okay? It's trying to do the reversal of the noise, basically, okay? So this is another view that given a image x, you choose a noise which is standard normal, obviously, and then you kind of scale that noise by sigma, okay? So it's not just x plus z, it is x plus sigma z. So it's kind of you added some noise there. So then your x plus sigma z became this this is slightly noisy, and then this score estimator is trying to predict the noise that you added, which is like z over sigma square. It is trying to kind of denoise that, okay? So that's the interpretation of this thing, okay? So it has a nice geometrical interpretation, okay? So how do we train eventually? So training scheme, here you will see all the terms are known to you, okay? You can always sample z from standard normal, and then you can form this this loss function. XL is known for various sequence of XL. The XL is the training data basically. So let's say there are L of them. So various, let's say clean image you take, and then you add some noise, and then you you try to denoise. So basically minus of ZL by sigma square. So ZL is known to you, sigma square is known to you. So then you kind of try to minimize this loss. Okay. So you can do this in batches again. Okay. And if you keep doing this for many clean images, you slightly denoise, and then you add the noise, and then there is a neural network denoise, and you keep doing it over and over again. Also, it's like although you went through all the training data, which is capital L, but it's not like you have to do it once. Okay. So because you have to go for the minimum theta. So you may have to do many epoch basically. Okay. So many epoch, many sweep through the training data, and this is another view. Okay. Take clean image, just noise, denoise. So one of the thing is like why this should make sense. Okay, and one of the result is way back from 2011, which says that the explicit score matching, where you do these kernel estimates for the score, is only constant away from this denoising score matching. So essentially, so basically we know that if we throw in very powerful kernels and so on, it will really approximate it really well. And the way we are using it via denoising, it is very similar to that. Okay, so they are not really that far. So yeah, I guess. So I had yeah, I think I ran out of slides. So I think what I will do is I will do the remaining things in the next class. So next class, the thing I planned was SDE based score matching, and I have to introduce you to ODE, ordinary differential equation. Some of you don't know, some of you are from maths, so you are pretty good with that. But anyhow, we need only first order ODE. So that's like very simple. And SDE is kind of a xt equals to xt minus 1 plus minus gradient. It's essentially a Euler step. If you know how to solve ODE numerically, then that's how you solve in a discrete setting. So this is the connection we will make, and we will see things in a continuous form. Okay, so basically now this process that we have, forward process, now it will be seen as some flow. Okay, or basically continuous flow, and this will be done via ODE. When we say continuous then process, then usually they are modeled by ODE. Okay, it's a simple ODE, dx by dt with some first order terms. So it is first order ODE we will be dealing with, and then we also need to do the reverse process as well. Okay, so there is a we need to know how to solve this in reverse time. So both way we can formulate that, but you can never get rid of neural network. Okay, so there also you will kind of need a way to do that, but it will be stochastic ODE. Okay, because we want to create the variation, so there will be this additional perturbation term always. Okay, so we ODE, then we go to stochastic ODE, and then we look at a slight variation of the Euler method, and then we have a form of score matching with SDE. Okay, and so that will take only 20 minutes of the next class, and then remaining class we will do some engineering. Okay, with text to image and various kind of architecture details and things like that. Okay, how to do further improvement and so on. So with that we will wrap up. So I'm kind of done for today's class. That's all I have. Okay, thank you.